So what we will do going forward is we're going to focus our attention almost entirely on covalent bonding rather than ionic bonding. And while we're talking about covalent bonding and shared electron pairs and thus bonds that we draw with lines, we need to make some distinction about bond lengths, which is simply the distance between the two nuclei of the atoms that are sharing a bond or sharing electrons. And then also bond strengths. What is the energy essentially required to break that bond or type of bond? So first, starting with bond length, that's simply the distance between the two atoms that are sharing the electrons. And the general trend here is that triple bonds are shorter than double bonds, which are shorter than single bonds. And hopefully this makes some sense. The more electron pairs are being shared between the two elements, the closer, the stronger the interaction, the closer the two nuclei are drawn to each other in order to share those electrons. So triple bonds are shorter than double bonds, are shorter than single bonds. And we can see this illustrated here if we look at kind of a series of bonds between two elements and the single, double, and triple variations. So a carbon-carbon single bond has an average bond length of 1.54 angstroms. An angstrom is 1 × 10⁻10 meters, or just 0.1 nanometers. And a double bond is shorter than this at 1.34, and a triple between carbon and carbon is 1.20 angstroms. Similar trends can be seen for the CN single, double, and triple bonds, for the NN single, double, and triple bonds, and for NO single and double bonds. And that trend will hold regardless of the elements. Now the second thing is bond strength. Now, turns out we've actually talked about bond strength before when we talked about bond enthalpy or bond association energy. These are measures of bond strength, how strongly held the two elements are to each other, how difficult it is to break them apart. And what we'll see the trend here is that triple bonds, while they may be the shortest bonds, they are the strongest bonds, followed by double and then single bonds in terms of breaking all three bonds or all two bonds between the two elements, or perhaps said a different way, in terms of the energy required to break both elements completely apart from each other. And hopefully this makes some sense. The closer the two atoms are to each other, the more electrons are being shared between the two, the more difficult it is going to be to pull those two apart. So we can see this sort of shown here in the average bond enthalpies in kilojoules per mole. You see a CC single bond at about 348, going all the way up to 839 for a CC triple bond. And this is, again, for breaking those two elements completely apart from each other. So not just breaking one bond of the three bonds, but breaking all three bonds. Similar trends hold for nitrogen, nitrogen, single, double, and triple bonds, and for oxygen, oxygen, single, and double bonds.